We know how to find derivative functions using the limit definition of a derivative. That's this guy right here, the limit of the difference quotient. But we're interested in finding shortcuts because calculating these limits is a lot of work. It's a lot of algebra work. So if there's a shortcut, I think we all want to know what it is. We're going to find a shortcut in just a moment. This shortcut will apply to functions that are essentially other functions being added together. For example, the function j of x, I'm letting that be created by two other functions, f and g, which I'm adding together. This will be useful because sometimes we need to take derivatives of functions that have multiple terms. And if that's the case, we don't want to have to create the limit definition for all of these terms individually. So this shortcut could definitely save us some time. We'll start by setting up the derivative function as a limit. So using j of x, that function that comes from adding f and g together, I've written out the limit definition for j prime. But since we know that j comes from f plus g, then we can find out what j of x plus h is. We can't really take it too far, but we can definitely say if we plug x plus h into j, then we're also plugging it into f as well as g. So we can rewrite that limit definition for j prime, where the numerator, instead of j of x plus h, becomes f of x plus h plus g of x plus h. And then instead of subtracting j of x, we're going to replace that with the f of x plus g of x definition for j. And then of course we'll copy over the h in the denominator. Now I've got some parentheses around the f of x plus g of x, and they are serving a purpose here. It's making sure we distribute our negative into each one of those terms. So I'm going to go ahead and distribute that and then rewrite our limit. Now that I've distributed that subtraction, I can see that I have f with x plus h plugged into it minus f of x in my numerator. They're just not next to each other. So maybe that's our next move, is to move things closer together. I'm going to pair together the f terms and the g terms in my numerator. So now I have f of x plus h minus f of x, and I also have g of x plus h minus g of x in my numerator. Now with fractions, we can split any terms added or subtracted together in the numerator, we can split them into their own fractions. So instead of writing this as one big fraction over h, I'm going to give the f terms their own fraction, and the g terms will get their own fraction. And we can verify that this is mathematically legal. Just by adding these two smaller fractions together, we would get back the fraction that we had before. The reason why I want to separate them is because we know we have a limit law that says that if we have a sum or a difference, we can apply the limit to each term in the sum or difference. So I really just broke the one big limit into two smaller ones. And if we look really carefully, we can see that each one of these smaller limits is actually a derivative itself. So in this blue rectangle, I have the definition for f prime. And then in this purple rectangle, I have the definition for g prime. So essentially what we just showed was that j prime is the exact same thing as finding the derivative of the f function and the derivative of the g function and adding them together. So this is great. I can find the derivative of each function individually and then add the results together at the end. We say that this is the derivative of a sum is equal to the sum of a derivative. It's really similar to the limit laws that we saw before, but here we're applying it specifically to the limit definition of a derivative. Technically, we can go through this exact same process for some generic function j that comes from the difference of two functions. The only thing that would be different is that between f and g we have a minus sign. And so when we split our big limit definition into two smaller ones, instead of adding those together, we would subtract them together. For the difference rule, we can say that the derivative of a difference is equal to the difference of two derivatives. Next, we'll look at the constant multiple rule. We're going to assume j to be some generic function, which looks like a function f that's being multiplied by some constant c. If we wanted to find the derivative for this j function, we could start with the limit definition, and then we'll replace j with c times f. So j with x plus h plugged into it would look like c times f with x plus h plugged into it. And rewriting our limit, replacing j of x with c times f of x, and then copying down our denominator. Now that we've made that substitution, we can see that every term in the numerator, there's two of them, two terms, has a factor of c. So the first term has a factor of c, the second term has a factor of c. Well, that means we can factor c out. And we know that with limits, a constant multiplied to something can be factored out. So we're going to take that c even outside of the limit notation. And then we see, if we look very carefully, inside of this blue box, we have the definition for f prime. And so what we essentially just said was that j prime can be found by calculating the derivative f prime and then multiplying it by c. So that's our constant multiple rule. If we're trying to take the derivative of a constant times a function, we could instead take the derivative of the function and then multiply by a constant afterwards. So we just went through three shortcut rules that say when calculating a derivative for a sum, a difference, or a constant multiple, we can just find the derivative of that more simple function and adjust it by adding it together, subtracting the two functions, or multiplying by a constant at the end. So let's practice using some of these rules. For the first function I have here, 3 times x squared, well, I'm going to look at this instead of 3x squared, I'll look at it as 3 times the function x squared, where we can find the derivative for x squared and then multiply it by 3 afterwards. Remember that for any polynomial, any x raised to the power of 2, for example, we just bring the exponent down so that it looks like 2 times x, and then we reduce the original exponent by 1. So 2 subtract 1, I'd have an exponent of 1. So the derivative of x squared looks like 2 times x. But remember that we have 3 times x squared, so we still need to multiply that result by 3. So if I take the derivative of 3 times x squared, that will be equal to 3 times the derivative of x squared for a final answer of 6x. So we really just let that constant multiple 3 hang out for the ride while we calculated the derivative of that polynomial function x squared, and then we brought the 3 back in afterwards to get our final answer of 3 times 2 times x. This next one is a little bit boring. Not sure why I put it in here, but if we took the derivative of x squared, we would just pull the exponent down like we did in that last example. So it would be 2 times x to the first power, or just 2x. Our next one, maybe we're getting the hang of it here. We hold the 2 for a moment, take the derivative of x to the 5th power. That would look like 5x to the 4th power. But don't forget we had a constant multiplier of 2, so it's really 2 times 5x to the 4th, which would be 10x to the 4th. That's our f prime. Let's try another one. 7x to the 5th power, that would become 7 times 5 times x to the 4th, or 35x to the 4th. And then for our last one, let's look at a sum and difference. Notice that I'm using two functions that we actually calculated derivatives for in this example. So if I want the derivative for this function, f, what I need to do is take the derivative of 3x squared, which we did in our first example. It was 6x. And then I need the derivative of 7x to the 5th, which we did in the previous example, which was 35x to the 4th. And that would be our derivative. 6x plus 35x to the 4th. Those are not like terms. We can't simplify any further.